All right, so we are working on recap number 2 for AP Calculus Bootcamp, and this video is going to talk about implicit differentiation, which we are going to use when we cannot solve explicitly for y. Maybe it's that we can't, maybe it's that we don't want to, maybe it's a lot of work. So that's going to be our first topic. Then we're going to apply that concept to related rates problems. Finally, then we're going to talk about the first derivative test, which will find increasing and decreasing intervals, allowing us to see maximums and minimums. And we'll talk about the second derivative test, which will find intervals of concavity, either concave up or concave down, also letting us find points of inflection. So to start, we would like to find dy dx, which means we're talking about the derivative with respect to x. So I'm going to start by taking the derivative with respect to x. Seems like a good place to start. Keep in mind that implicit differentiation is a version of the chain rule. Anything that is not our variable that we are taking the derivative with respect to, which in this case is x, we are going to assume is a function of that variable. So we're going to have to think about the whole inside-outside kind of feature with each one. So to start, the derivative of x squared with respect to x is just 2x. This next one, I'm going to think about this as being negative 5x times y. So when I take the derivative of this term, I'm going to need to use a product rule. So I'm going to say this is going to be the first times the derivative of the second with respect to x plus the second times the derivative of the first with respect to x. Then this term, 3y squared, I'm going to take the derivative with respect to x. So it's going to be 6y using the power rule. Technically that's to the first power, times the derivative of y with respect to x. That's that chain rule coming in there. So we think about taking the derivative of the outside, using the power rule, leaving the inside alone, times the derivative of the inside, which is dy dx. All of that then will be equal to the derivative of 7, which is just 0. So we've taken the derivative, but the question is asking us to find dy dx. So I have a dy dx with this term, and I have a dy dx with this term. So I'm going to move everything that does not have a dy dx over to the other side. So I'm going to have negative 2x plus 5y. Now, using some algebra skills, both of these terms have a dy dx in them, so I'm going to factor out dy dx, and we'll be left with negative 5x plus 6y. So then to get dy dx all by itself, I just need to divide by negative 5x plus 6y. So here I have dy dx equals this quotient. Alright, the next problem then, we are still taking the derivative with respect to x. We have some exponential functions in here, which if we remember our rules, the derivative of e to the u is simply e to the u times u prime. So the derivative of e to the cosine of x with respect to x is going to be e to the u times the derivative of u with respect to x. Since our variable here is x, the derivative of cosine of x is just negative sine x. Then I'm going to add to that e to the u times the derivative of u with respect to x. So that's going to be cosine of y, right? So derivative of the outside, leave the inside alone, times the derivative of the inside, which is dy dx. All of that will be equal to the derivative of 1/4, which is 0. Again, I'm not asking to just find the derivative. I want to isolate dy dx and solve for that term. So I'm going to move the sine x, or the negative sine x, e to the cosine x to the other side. So that should be an x. Then I'm going to divide by e to the sine y cosine of y. You'll notice that in both of these problems, the final answer are dependent on both x and y, and that is okay. If you see it as a differential equation, you just know that your slope field is going to be dependent on both variables. All right, so now let's think about this similar concept, just a little bit different of a question. Find the coordinates. So coordinates would imply point xy of the 2 points on the curve where the line tangent to the curve is vertical. All right, so if we think about line tangent, you should be thinking about derivative, right? And we want that to have a vertical slope. Well, a vertical slope would be undefined. So really what this problem is asking us to do is to find the coordinates in which the derivative of this curve is undefined. All right, well, step 1 then is going to be to find the derivative of this curve with respect to x. So I'm going to go 2x minus 2 plus 8y dy dx plus 16 dy dx plus 0 equals 0. Hopefully that derivative is looking okay to you. If you have questions, maybe write down a little star next to it and see what you can ask tomorrow in class. But we're going to isolate the dy dx. So I'm going to have added the 2 to the other side and subtracted the 2x, and I will have divided by 8y plus 16. Think about that for a second and make sure that all of that is sitting okay with you. Still good? All right. So all of this then can be simplified a little bit if you want to. Okay, so thinking, oh, that was my fault. Thinking about taking out a 2, we are currently here. So now, this question was asking for where our slope is going to be undefined. Well, if we look at this quotient right here, we know a quotient in mathematics is undefined if the denominator is equal to 0. So 4y plus 8 being equal to 0 means that y is equal to negative 2. So if we're talking about, they told us it was going to be 2 points. We are looking for 2 points in which y is equal to negative 2. Using our original curve back at the top, I run out of room to write here. Hopefully I can be able to see and write at the same time. X squared minus 2x plus 4. We know that y is negative 2. We are looking to then find our x values that go with it. So, a little bit of algebra. Negative 2 squared is 4. 4 times 4 is 16 minus 32 plus 1 is equal to 0. That's going to leave us with x squared minus 2x minus 15 equals 0. A little bit of algebra factoring. Things that multiply to negative 15 and add to negative 2. We know it's going to be 5 and 3. 5 is more powerful. So that results with x being 5 and x being negative 3. So again, the key on that one is to break it down really step by step with each question and understanding what you are being asked for. All right, I think in your packet you might have some answers written. These are just typed out solutions if you wanted to look at them, or maybe you chose to not listen to the video at all and just do the problems yourself, but there's basically the same explanations just without my voice. All right, so next then we're going to talk real quick about related rates. If you remember from related rates, we are talking about what happens later, and there's a wonderful related rates video still on our website from Andrea Lemke and myself, so you can go back and watch that if you need a more intense explanation. But if we go through and just talk step by step, we're going to think about our volumes, areas, surface area, which technically is area, and we're going to talk about how they're changing at a certain time or a certain instant. So we have that an inflating balloon is spherical in shape. That's going to be important to us, and its radius is changing at the rate of 3 centimeters per second. So the radius is changing at 3 centimeters per second of our spherical balloon. Okay. At what rate is the volume changing? So how is our volume changing? later when the radius is equal to 10 centimeters. All right, well, before we can start thinking about these derivatives, we have to have a way to relate our variables. So the volume of a sphere is going to be 4/3 pi r cubed. Now, if I want to set this thing in motion and start this balloon blowing up, I'm going to take the derivative with respect to time, so we get our rate. So this side is going to be dv dt. On this side, 4/3 pi just kind of hangs out, it's a constant. Then the derivative of r to the third with respect to time is going to be 3r squared times dr dt. Well, if we look now, dv dt is what we wanted to find. We know that it's later, and r is going to be equal to 10. And we know that dr dt was equal to 3 centimeters per second. So we still have our 4/3 and our pi equal to our variable that we're talking about. So those 3's are going to cancel. This is going to be 12 pi times 10 squared equals dv dt. 10 squared is 100, so we're going to have 1200 pi dv dt. And be careful with units. So we're talking about the rate of change of volume, and we know that volume is measured in cubic units in relation to time, and our time was measured in seconds. So you can use these variables. The v here corresponds with how we would measure volume, and the t here corresponds with how we are measuring time in this particular related rates problem.